Equilibrium in a nutshell. So what is equilibrium? Basically what happens, some reactions are what's referred to as reversible. That means they can go forward and then they can come back and start producing reactants again. So they're producing products and reactants. The key feature of equilibrium reactions is they never go to zero in terms of the amount of reactants. So a typical reaction, it goes to completion, all or one of the reactants called the limiting reactant, and you're left with products. And then typically an excess reactant if you didn't measure quantities properly. For equilibrium, that never happens. You never get to zero. You will have some reactant at the end no matter what, of both reactants. If there's multiple, then multiple reactants. So they never zero out. And the key feature is you get to the point of reaction where your rate of production of product is equal to your rate of production of reactant. So you're referred to as being equilibrium. The way you recognize equilibrium reaction is with a double arrow. Whenever you see a double arrow, that's a key feature of, okay, this is equilibrium reaction. The thing that makes these difficult is that this prevents you from using stoichiometry. So for stoic, usually you have quantities of one chemical and you could go between reactants, you go between reactants and products. You can move around pretty easily just using ratios. Here you can't. You could go between quantities of products at equilibrium. You could do stoic between products, but that's it. That's the extent of what you could do in terms of relationships between chemicals. You can't go, okay, I have 5 grams of reactant, so I have to have X grams of product. No, that doesn't work. And the reason for it is because not all these reactions go to completion, which means only a portion of them are produced. So you can't assume that out of 5 grams, 4.8 became product, that 5 grams become, you have no idea. So that's what makes these really complicated. So this is an example of an equilibrium type scenario. The rate of the forward reaction is equal to the rate of the reverse reaction. Stoic can be used for this. So what's going on in this particular situation, you have N2O4, which is this particular chemical. So you have N2O4 producing 2NO2. So this is the reversible reaction that you're looking at. And the key feature you'll notice from this reaction is the fact that you can go both ways. The arrows are equal length. That's another little small detail you want to pay attention to. When the arrows are equal length, they usually imply that the reaction can go at the same rate, both directions. Sometimes you'll see a long arrow going one way and a small arrow going the other way. That implies that one direction is favored more than the other. So those are the little details you're supposed to figure out. So in this situation, what you would see is you have N2O4, you would have just a clear solution. Now, what happens if you start favoring the products? Well, you start putting this little brown chemical, which as you can see is NO2. And as the reaction keeps on going toward products, the amount of NO2 increases even more, and you start producing a lot more of it. Graphical representation of equilibrium. So what's going on here, there's two chemicals, obviously, two sides of the reaction, I should say. So one of these is reactant, one is product. So how can you tell which is which? Well, you should know the amount of products will start at 0, right? You haven't made any at the beginning. That's why this line will represent the products, because it's increasing over time. So you have CO2 or H2. The reason either or is telling you that those two products are produced, and the concentration of them, from here you would assume that they're 1-to-1 ratio, and that's the only way this would work, is that their concentration is equal to one another. Whereas on this one, this is your product, this is your reactant, and it's H2O or CO, basically implying that there's a 1-to-1 ratio between them. So you can actually figure some stoic into the scenario. What I mean by that is that if there was, let's say, let's say that your reaction hypothetically was CO plus 2H2O, which this is completely not balanced. So it's just a random scenario on this. So you see how you need 2H2O for every CO for this reaction. If that was the case, then your concentration of H2O would be lower. And the reason the H2O would be lower is because you're using more of it as part of the reaction. So you would expect it to be consumed faster than the CO. When you see the line the same like this, you're assuming that they're 1-to-1 ratio. So you could actually figure out the stoic, if you will, of the reaction, the coefficients, but you can't use stoic to go between chemicals. That's the real weird thing about this. But you could figure out the balanced reaction if you have this kind of data for the most part. What you're going to see here As you get to a point where you see how it starts going horizontal, that's your point of equilibrium. So at this concentration, you're at equilibrium. So say hypothetically, this is like, 0.5 molar. This is this 1.0 molar. So you can get the equilibrium concentrations of the chemicals using a graph. And they'll do that to you, just FYI. Like you have your initial concentrations, like let's see, looks a little bit higher than, it's about the same. So let's assume this is 1 molar, which is really rare. And it's obviously 0. So you have your initial concentration is 0 and 1 molar, and the equilibrium concentration becomes 1.0 molar and 0.5. All theoretical, hypothetical scenarios, right? But you can get that data from a graph if you wanted to. So equilibrium reached when the concentration levels out, so when it goes horizontal. The concentration involved, the chemicals never go to 0. You notice that the reactant doesn't zero out ever. And that's always going to be the case. So be aware of that. You don't zero out your reactants. All right, equilibrium constant. This is a numeric representation of the equilibrium reaction. So you write what's called equilibrium expression. We'll talk about that in a second. But your K, which we've talked about before, is your equilibrium constant. And you calculate that by putting the ratio of products to reactants from the reaction at equilibrium. So after you reach equilibrium, what's the ratio of the products versus the reactants? That gives you your K. Now, there are many different types of K. So before you freak out, why are there different types of K? It depends on the unit you're dealing with. What I mean by that, if you're dealing with concentration, you're going to see Kc. They could also call this Kq. They could call this K. It's interchangeable. The K, Kc, they're kind of all the same thing. The ones that you have to really pay attention to are Kp, this is for pressure. So whereas Kc, you represent the chemicals, concentration with brackets, but Kp you don't. You put P in the place of brackets. If you put brackets for a Kp question, you'll be marked wrong. You can't do it. So your Kp values have to always be in terms of P, and we'll go over some examples of that so you can see what that looks like. Ksp is when you have a solid as a reactant. So anytime there's a single solid as a reactant, it's a Ksp question. Now, be aware, Ksp questions are basically insoluble substances. So if you remember your solubility rules, like AgCl, it's insoluble, right? Well, it turns out it is slightly soluble. There's a little bit of dissociates, and that quantity can be determined using Ksp, which is the solubility product. We'll talk about Ksp a little later, but just be aware that it refers to a substance that's a solid, so insoluble substance, which should not dissociate, but it does dissociate ever so slightly. And you can see some ridiculously small numbers for it. K is when you're talking about acids, so it's equilibrium constant for acid situations where you have acid dissociating. Kb is dissociation for a weak base. So these are the important ones, the Kp, Ksp, K, and Kb, because it gives you very important information. Kc is the only weird one because Kc you could technically use for like K. You use Kq, they're interchangeable, but Kp, Ksp, Kb, they're unique. That means when they give you that piece of, or they ask you for that, they want something specific and you have to interpret it specifically. And finally, Kw, this is the ionization constant for water, which is basically the dissociation level of water. So water breaks apart into hydrogen gas, H2O and OH. And what you're going to represent, or the math that's related to that, is this. So here's what this looks like. You have H2O. It's not really dissociating. It produces H plus, or you can call it H3O. They're interchangeable. We're going to call it H plus and OH so you can see it's balanced pretty easily. If I make it H3O, then you have to go back and balance it afterwards. So the concept here is that whenever you have the water, your H plus and OH have to equal to 1 times 10 to negative 14. So when you take the concentration of H plus times OH minus, it will always equal 1 times 10 to negative 14. Which means your pH, and we'll talk about pH a little later in next unit, is equal to 14, which means that these two for neutral water will be 7 and 7 as far as their pH values. And we'll talk about pH a little later, but I just want you to understand that's where Kw is going to go eventually. So let's try some expressions so you can see where the concept's going. So for this, we have gases. Now, they could theoretically ask you for Kc. For gases, the weird thing is you could do a Kc for it. You could put this in brackets and you could, set it up that way. But if they ask you for Kp, you have to do something specific. So let's say they ask you for Kc for the sake of argument. So your Kc is going to equal to the product of reactants. Now, you're going to ignore solids and liquids. Anything that has an S or an L is not written to the expression. You just pretend like it's not there. And your coefficients for the chemicals become the exponents. You notice it's products over reactants. And I put it in brackets because we're doing Kc. That's important. You want to make sure you're aware of this. So don't write solids and liquids and products over reactants, and your coefficient become exponents. And if they're asking for Kc, you have to use brackets. Now, what if they're asking for Kp? You can't do brackets. If you do brackets for a Kp question, you can get marked wrong. So what do you do instead? You put P and you raise it to whatever exponent, and then the chemical, you put as a subscript. Same thing with this, P, CO, and this is going to be to the second as well. So that's your Kp expression. Very important you understand this. You cannot do Kp with anything except P's. If you do anything else, they're going to mark you wrong. If they ask you for Kp and you decide to do brackets, you just got dinged. So be careful. This is obviously a KSP question. So I'm just going to say KSP is equal to, now you could do this as concentration or product. Now KSP typically is going to be in brackets. So I'm just going to put this one in brackets. Solids are ignored, right? So that's why it's nothing there except just CO2. So that's your expression for it. All right, for this one, Kc will be the best bet because their ions in solution or aqueous would be Zn 2 plus brackets, Cu 2 plus brackets. You're done. So that's what it looks like. Now, what about calculating this stuff? Well, you have this reaction. You have SO2 is produced plus O2 produces 2 SO3, and they're giving you the concentration for both chemicals. So what do you need to do first? All three chemicals is write your expression. And your expression for this is equal to this. SO3 second, SO2 to the second, O2. And then what I did here is plugged in the numbers where the setup is. It's extremely important you do this first before you plug in numbers. Why? Because one, you want to avoid having any brain farts where you set up the wrong values. And two, more importantly, you want to make sure the reader, the person who's looking at your answer, can follow your logic. So when you write the expression, it just really clears a lot of things up. And it helps you avoid, silly mathematical errors, which are very typical for this kind of question. So mathematically, what you should do, square this number, get a value, square this number, times this, get a number, and divide top by bottom. What you should not do is try to do all at the same time on your calculator. Now, if you're very skilled with the parentheses on your calculator and you know how to do multiplication division really quickly with it, fine, go with it. But for those that have a tendency of making sloppy errors, which this is the way it would work out. You'd say this divided by this, and then you put times this in your calculator because that's what it looks like, right? Your calculator interprets that as saying, oh, okay, this and this, you divide this by this because it's on top of this. But when you say multiply, you're implying this is on top. And that's going to give you a whole different number. So that's why you don't want to do that. So multiply top, multiply the bottom, then get your answer. So there's your answer. Look at that K, it's gigantic. So this reaction is very, very, very spontaneous, right? The bigger your K, the more spontaneous it is. It's greater than 1, so right off the bat in your mind, you should be like, okay, G is negative. And you could actually extrapolate this even further by looking at the reaction and saying, wait a second, there's 2 moles of product, and you're going to assume all these are gases. Even though we did it as concentration, these are all gases. You could do, once again, gases as concentration if the scenario allows for it. In this situation, it did because they give you molarity. So these are all gases. So you have 3 moles going to 2 moles. So your entropy should be negative, right? You're going toward more order. And as a result, your entropy is going to be negative. So that means that your driving force for this has to be your enthalpy. And for those like, what the heck? How did you get to all that? Well, here's the reason. Remember this formula? So if we know this is negative, negative times negative makes this a positive coming from here, right? And we know this is negative for sure. So what's the only way this can become negative? Your G. Your enthalpy has to be negative as well. That's your driving force. So connecting back to thermal world. All right, going between Kp and Kc. So sometimes they'll ask you for the Kp and after they give you the Kc and vice versa. Just requires this equation. So all you have to do is just plug and chug. So Kp is your partial pressure constant. Kc is your mole concentration constant. R is that. Temperatures in Kelvin, always Kelvin, not Celsius. And your change in N is basically your moles of product gas minus moles of reactant gas, not moles total, gas only. If there's liquids and solids, we don't care, right? All right, so what does the value of K mean? The bigger it is, the more it favors products. So if it's greater than 1, you're favoring products. And it's a mathematical thing. Because remember, your K expression is products of reactants. So if your value is greater than 1, that means you have more products than reactant, which implies you're favoring the products, right? If your K is less than 1, you're favoring the reactants, which means reactants want to go forward. And your G is negative, of course, if your K is greater than 1. If your K is less than 1, the reaction favors the reactants, and your G is positive. For reversible reactions, you can actually figure out the K of the opposite direction. So if this is the K for the forward direction, say products of reactants, what would the K for the reciprocal be? Now, if you look at this reaction, you could just say, okay, it's products of reactants again, then you can just plug in the numbers and get the value. Or you could remember that, you know what, if this is the K for the forward reaction, inverse reaction is just going to be the reciprocal of that, so 1 over K. So this is a twist between this and, let's say, Hess's law. When you flip a reaction for Hess's law, you change the sign from positive to negative or negative to positive, right? For K expressions, you don't change signs. You mathematically do something to them. So if I flip the reaction, it's going to be the reciprocal of the reaction. What if I double the chemicals? Let's say instead of having 1 and 2, what if I do 2 and 4? Well, I double the quantities, right? You multiply both by 2. So what do you do to your K? You raise it to that power. What if I half the chemical? Well, what's the K raised to 1/2? Because that's what you did, right? Whatever you do numerically to the reaction, you will create that as your exponent for the K. Well, what's 1/2? K to the 1/2? Square root. That's what 1/2 means, basically, right? So that's how the math plays out. So for example, if your coefficient increased by 3, then your K would be K to the 3rd. If you have them by 2, the K would be 1 to the 1/2. So whatever factor you change it to, that's what you're doing to the K. So what about multi-step reactions? What if you want to figure out a K for a multi-stepper? So here's a multi-step reaction. You're trying to figure out the K for this, and they give you this. Shades of, electrochem when you're doing redox reaction, you're trying to combine the two. Oxidation reduction reaction, look at the final, Hess's law, all those are in play. Same thing conceptually as far as you cancel out what's our opposite sides, but what's different is you don't add or subtract, you multiply and divide. That's the big difference. So here's your reaction 1. Here's reaction 2. So what I did, I took this chemical and I kept it as is. Now, why did I keep it as is? Because I need HCrO4 on the reactant side, just like Hess's law, same exact concept. Then the second reaction, what did I do? Well, I need calcium chromate on the product side. So what I need to do is flip it. Now, when I flip the reaction, reciprocal of the K, and that's what I did here. So your K is equal to Ka times 1 over Ksp, because you multiply those two. The way to do that is to do 1 over this, get a number, and then just multiply whatever numbers you are. So that way, right now it looks weird because it looks like I'm doing that divided by that, but what I'm really doing is multiplying this by whatever the value of this is. So your call how you want to handle it, but just remember, multiplication, division, there's no addition or subtraction. So now you have to make a distinction between electrochem questions, thermal questions, and K questions. All of them handled differently. All right, let's try one more. So calculate the value of K for this reaction. So you're shooting for this, and you have these. Okay, so we're going to handle it just like we do Hess's law. Look at the first reaction. Okay, I want N2O. Is that the only source of N2O here? Yes, it is. So I'm going to flip it. Now, if it wasn't the only source, I would ignore it for now, and I'll come back to it later. So 2N2 plus O2. So because I flipped it, your K is going to equal to 1 over 1.2 times 10 to the negative 35. Which is going to give you a very large number because your value in the bottom is really, really small. So you're going to get a big K. All right, next reaction. Do I do anything with it? Any N2O4 on the product side. So I'm going to flip that. So 2NO2 N2O4. Now, is that the only source of N2O4? If you notice, it is the only source of N2O4. So here's the bad news. You got to deal with the coefficient because the coefficient for N2O4 should be 2, but you have 1. So that's not going to work. So what do I need to do? Multiply this by 2. So I get the right N2O4. 2 times 2, by the way, is 4, not 2 again. So now for your K, remember we flipped it. So it's 1 over 4.6 times 10 to the negative 3 squared. And the reason we square is because we doubled, right? When you double, it's automatically you raise it to that power. Whatever you do to the reaction, you raise it to that power, and now you have to do the reciprocal because you flip the reaction. All right, and the third reaction, what do we need to do? Well, we need to have O2 on the reactant side and 2 and O2. Nothing here that's in the final reaction, so it's going to be a cancellation situation. So what I need to do is arrange it so the chemicals I don't want go away. So what do I want to go away? Well, based on this, I actually want O2 to be in the final reaction. And according to this, it's not at this point. So what do I need to do? Well, there's no O2 on this side, so I'm going to put O2 on this side. So I'm going to put N2, so 2O2, dun, dun, and 2NO2. The reason is that you need to have 3. Right now, all my O2 is on the product side. So I have to keep this as is to balance it. Also, I need to get rid of the NO2, right? So now what do I do? Well, you look at it and you realize that you need to have 2 NO2 to cancel out this. So I'm going to multiply this by 2. And all I did to the K, I then do the reciprocal, right? So I'm just going to do 4.1 times 10 to the negative 9. I raise it to the second power, so squared. So now do this, and then cancel those opposite sides. So you have 4 NO2 on this side, 4 NO2 there. They both go away. O2, I have 1 here, 3 here, because 1 minus 4 is 3. And 2, 2, and 2. So I'm left with 2 and 2O plus 3 O2 produces 2 and 2O4. Exactly what I was shooting for. And now all you have to do mathematically is do 1 over this, get an answer, 1 over this squared, get an answer, square this, get an answer, and then multiply all 3 of those together, and you get your final value. So you can play with that in your calculator to make sure you understand it. All right, reaction quotient. It's just like K, except it deals with initial concentrations, not equilibrium. So K deals with equilibrium. So this is what happens when that level, when the reaction levels off and goes horizontal. Q is before you even start. What's your initial concentrations? Same concept as proxy reactants again. It allows prediction of which direction a reaction favors or whether precipitation occurs. So this is where Q comes into this whole conversation. Typically, you'll have a K or you'll solve for K, and they'll ask you, okay, based on these concentration, will there be a precipitate? Or which way is the reaction favor? And the way you figure that out is you solve for your Q and compare it to your K. And depending on what's bigger, you can tell if you favor the proxy reactants. So the best way to visualize this, pretend Q is your reactants and K is your products. If your Q turns out bigger numerically, you're going to favor the reactants. If your K is bigger numerically, you're going to favor the products. And that's the way you want to interpret it mentally to make this a little easier. So here's a typical reaction. It's a KSP question. You know it's silver chloride. You know it's insoluble. But here, you can do some calculations related to it because some Ag and Cl is going to be produced. Let me just do a Q for it real quick just so you can understand. So your Q for this would equal to Ag plus Cl minus. Looks just like a KSP question. I mean, it is a KSP, right? But you're solving for Q for this because you're looking for initial concentration. That's all it is. Products over reactants. So once again, we ignore solids because it's the reactant side. So we'll talk about what to do with Q in a second, but let's go over some general ideas. If your Q is bigger than K, the reactant is favored. Remember, Q is your reactant, K is your product. If your K is bigger than your Q, then you favor the product side. So that's what you want to visualize mentally. So let's do some math. Use the chemical constant and initial concentrations below to determine whether a precipitate will form. So this is a very common angle. Will precipitation occur? Whenever they ask you will precipitation occur based on concentration, your mind should be like, okay, it's Q versus K. It's Q versus K, because that's what it is. They gave you a K to make this even more obvious, and they give you concentrations. So all you have to do is solve for your Q. So your Q is 12. That is bigger than your K. Remember, Q is reactants, K is products. If your Q is bigger, you favor reactant. What's on the reactant side? A solid. So if you favor a solid or favor a reactant in a KSP type question, which is a solubility product question, then you can assume that you're going to precipitate. That's how you would interpret it. If the K was bigger, then you would favor the products and there will be no precipitate. So when that's your precipitation, you're really asking Q versus K. That's the end story for this. All right, let's try another one. The value of KSP for PbCl2 is 1.6 times 10 to the negative 5. Determine whether a precipitate would form if 100 milliliters of this is added to 100 milliliters of this. This is a very, very challenging question. Here's why. It's a dilution question. It did not imply that the volume is negligible or constant. So what you have to assume is that once you mix these two solutions together, you're going to change your overall concentration. Why? Well, you started with 100 milliliters of each, but when you mix them together, now you have 200 milliliters. Remember, molarity is equal to moles over volume, right? So your concentration as a result, you're going to have the same amount of moles for each chemical that you started with. That's not going to change. But the volume you're dealing with has changed. So your concentration is going to change. Is that important? Yeah, it is. Because in order to do the math for this, in order to solve for the Q, you would need to use the correct concentration based on the conditions. So when they give you two volumes and two molarities, it's a dilution question, which means you're going to have a lot more challenge on that question. So the first thing I'm going to do is write the reaction out. So it's lead chloride, and what's the only thing that can happen on a KSP question? You produce the ions. Notice I did balance it, 1 to 2, just like you would expect. All you have to do for a KSP reaction is take the solid, and remember, these are always insoluble substances. So if you know your solubility rules, you should recognize them really quickly and just associate them. And make sure you're balanced, right? Your charge has to be balanced and the number of each element has to be balanced. Usually when you do one, the other happens with it. So your Q is equal to Pb2 plus Cl minus squared. Remember, your coefficients become the exponents for the expression. I always write the expression first. So what I'm going to do is figure out my moles of lead. Why am I going to figure out the moles of lead? Because the two chemicals I need to solve for are lead ions and chloride ions. I don't care about the nitrate. I don't care about the sodium. So I'm going to start with the molarity of the lead nitrate and go using stoichiometry within a compound to moles of lead. So here I multiply the molarity times the volume. You have 0.4 moles of lead nitrate. I'm going to take that. I'm going to go to moles of lead. For every 1 mole lead nitrate, there's 1 mole of lead. So how many moles of lead do I have, lead ions? 0.04 moles. I'm going to do the same thing with the chloride in a second. But before I do that, I'm going to figure out the molarity of my lead in this current situation. So my current molarity is 0.2. This is what I'm going to use for my Q for the lead ions. Extremely important you do this. If you don't, your whole question is wrong. So let's go to the second part. We're going to do the same thing for chloride. Multiply the volume to the molarity, 0.02 moles of NaCl. There's 1 Cl for every mole in Cl. Do you have to do? Yeah, you want to show this. You want to make this very clear This is what's going on. Here's my math, because this is where the point's going to come from. So if you just decide to do this in your head, like, go from here to here without doing this little relationship thing, it's silly. Don't do that. You're thinking of it, just write it. It'll take you less than 10 seconds to do so. Your molarity in solution is 0.02 moles divided by 0.2 liters. So your molarity is 0.1 mole of Cl minus. So my Q now, I'm going to plug into the expression. So Pb2 plus is that. Cl minus is that. Remember, it's squared according to the expression. That's why we want to write the expression first. You don't forget that detail. So my answer comes out to 2.00 times 10 to the negative 3. That's my Q for this. My Q is bigger than my K. This was my K. This is my Q. So because it's bigger, you have a precipitate. So that's how you use Q versus K in the question. And this is the most complicated because there's dilution occurring on top of everything. So if you can do this, you could do any Q versus K scenario. All right, equilibrium. Now let's get to the heavy duty stuff. So we talked about precipitation. We talked about multi-step reactions and what happens to your K. Now we need to go into the math part. So I'm going to tell you in advance, the best and really only way to solve these questions is by organizing your information. That's going to require what's called a Rice-A table. You see some references call it the icebox. I call it Rice-A because the first thing I do is write the reaction. That's the R. Then your initial is your I. Your change is your C. Your E is equilibrium, and I added an A for answer. Why? Because for whatever reason, students will do all the calculations but not get an answer at the end. Like they do the math, but then they forget what's being asked. Don't answer it, and they lose all the points. It's like, really? So that's why we have the A part. So the thing you need to understand about these, if they ask you for K, you know you can't have for X. It's either one or the other. You can't solve for K and X together. So what I'm trying to explain to you is that if they ask you for a K on a question, your mind should be like, I do not have an X. I do not have an X, which means you need to interpret the data to solve for all the variables so you don't have an X. You cannot have an X and a K. So anytime the question asks you for a K, your mind should be like, okay, I have the concentrations for everything I need. Otherwise, I'm screwed on this. Same thing, if they give you an X, then you know you have to have a K. There's no way. You can't solve for both variables. So just keep that in the back of your head. Other key is that you must make a chart to organize your information unless the question involves KSP. For KSP questions, don't do a chart. It will just make things more difficult for you. So we're going to do those without a chart. All right, so the Rice-A chart, here's what it is. Reaction, initial condition, change, equilibrium, answer. You just call it Rice-A. And yes, you would have to do it for every equilibrium question. What happens if you don't? You just made a stupid mistake. You lost all the points. Don't do that to yourself. It takes a little time to get accustomed to it, but once you do, you realize it makes your life easier, not harder. So there are 4 types of questions. 3 involve solving for X and 1 solving for K. So what do you think the majority of the time? You're solving for X. So type 1, solving for equilibrium constant. You can tell this type by noting that they didn't give you a K. So notice this one, there is no K. So what do? What I'll do is get molarity for everything I need molarity for. So they give me a volume, they give me moles of the 2 chemicals, and they give me equilibrium concentration of this. This is why the chart's your best friend, because this goes in the E part. And without it, you're dead in the water, so don't do that. So the molarity of each compound is just 1 divided by 4, because they're all 1 moles, and it's all in 4 liters, so 0.25 molar. There's my chart. I put the chemicals they gave me. If they don't give you values for something, they're zeros. Simple as that. Your products typically should be zeros. Are they always going to be? No. Sometimes you have what's called a common ion scenario, where you have concentrations for a reactant and a product. We'll deal with those when we get to it. For now, if they didn't give you a concentration, assume they are 0 and fill out all the information you have. They gave me an O2 is 0.230, excuse me. So I'm going to put that in. Now I'm going to use my head. What do I mean by that? I'm going to start doing my adding and subtracting of X's. So we're going to determine which side we add and subtract X. So your change part is really X's. How many X's you add or subtract depends on the coefficient in front of the chemical. If the coefficients are 1, it's just X. But what if they're 2 or 3? Then it's 2X and 3X. That's where your mistakes are going to happen. Forgetting the coefficient. So that's why it's imperative you're consistent in your routine. So in this situation, all the coefficients are just 1, right? So, and this part, it's always going to be x, guys, always. Without fail, this is the x section. Your change is your x's. So minus, minus, plus, plus. So how the heck do I figure out what my minus and plus is? Logic. There's two different things going on that should help you figure this out. And this is where the brain teaser part of this thing comes in. You started with 0. You can never have a negative concentration. So this side has to be plus x. You cannot make this negative x no matter what you do, because you can never get a negative concentration, period. So if you have zeros, that's always going to be your plus x side. That's the simplest rule to apply to. Second thing you should have thought about is, how did I get from here to here? Did I add or did I subtract? Can you go from 0.250 to 0.230 by adding? Heck no, you're subtracting. So that's what you do. So this part, all you're doing is taking what's here and writing it down. This is 0.250 minus x, 0.250 minus x. 0 plus x is just x. 0 plus x is x. So all you're doing in this line, this equilibrium line, is bringing what's above it. That's it, nothing else. And your answer part is whatever's at equilibrium. If you're looking for concentration equilibrium, this is where the numbers go. So there's your setup so far. Now, I'm going to solve for x. So 0.250 minus x equals 0.230. Common sense, right? You could have looked at this in your head and said this is 0.20. 0.020, but we're not going to do that. We're going to actually do the calculation because we want the reader to know, hey, we know what we're doing. We're not guessing here. This is not luck. So now I'm going to plug in my values. So this is 0.230. It's 0.220. Why? Because when you subtract the value from each of these, that's what you get, which is 0.02. And then your x, well, you just plug in the numbers. There's your chart. Do you do two charts? No, no, this is all in one chart. I'm showing you into different phases. So please don't sit there, write one chart at the top and underneath do all the, no, all in one chart. You're just going through it. Then you write your expression. Always write your expression. I don't care if you can do it in your head, write it down. So for this one, I wrote it down, then I plugged in my numbers. If I ever see numbers without a setup or formula in advance, you know what's going to happen. So 0.00756 is your value when you do the math. Is that k greater than 1? No, it's less than 1. So what can you assume? Your g is positive. See the correlation, how fast you can make that? You can even figure out, in this situation, it's 1 to 1. It's 2 to 2, sorry. Gases in each side, so entropy is negligible. So you can assume in this situation there is no joule driving force because the g is not negative, right? It's not going to be negative. So you can't interpret your h from this, is what I'm trying to tell you. Finding equilibrium of all species by taking square roots. So this is type 2. So if they are looking for your k, this is the type you're doing. This is the one type, right? You just plug and chug the different variations. There's different coefficients and all that stuff, but the theme is the same. You're solving for x. The rest of these, you're not doing that. So you're trying to figure out the equal concentration of all species, whereas the last one you're looking for k. Sorry, you're not looking for x first. You're looking for k. What you're looking for this, you're looking for x. So the above reaction is the equilibrium constant of 6.9 and 1.10 BRCl. Introduced into 500 milliliter flask. So we could do our typical setup, waiting for your concentrations, because they didn't specify whether they want Kp or Kc. We're just going to go with Kc because we have the values we need for concentration. Once again, plug and chug. These are zeros because they didn't give us anything. Here is where the brain fart's going to happen if it happens to you. Not paying attention to the coefficient. This is minus 2x. Why is it minus? Because remember we said about zeros, you can't have negative values. So this is going to be your plus x side automatically. So now I'm going to do is just carry these values down into these lines. Now, write my expression, always. Plug in my numbers. Now, you'll notice that squared, squared. What you can do now is square root both sides. That's what the perfect square question is. You recognize these because both the top and bottom numbers are squared. Whenever that happens, you do this. So you have to look for it. So we take the square root of both sides, we get 2.63 equals x over 0.2 minus 2x. Distribute the 0.2 minus 2x to both sides. We start solving for it. Now it becomes an algebraic equation. So we're going to solve for x, so x is equal to 0.0840. This is where it happens for most students. They'll stop here and say, there's my answer. That's not what they asked for. They asked for equilibrium concentration. So what you should have, or what you will need to do, go back and plug in the numbers. Everything, plug this in, get a value. If this line is empty on a test at the end, you screwed up. Simple. All right, tech 3, determining the concentration using quadratic. Extremely rare. The quadratic is the most rarest. Literally one time in 40 years, they've had a quadratic question on the AP exam. And I think they're just doing it that year because they're annoyed at the students or something. I have no idea. They're like, oh yeah, you think you could always assume you can't do quadratic? Watch this. For our purposes, I'm going to show you how to do it because it's in your best interest. What you want to do is program your calculator to be able to do the quadratic. If you just Google your calculator, there's a formula, especially if you have a TI. It'll tell you what the formula is. You plug it in, you program it, you just plug in your ABC values and you're done. Now, if you don't have that, then you have to go through the steps of actually showing all the numbers and calculating, which is a little bit more pain in the butt. We're going to go the long way because we have no choice. So I'm going to plug in all my numbers. Notice once again, 2x, this is where your brain fart's going to be. 0.2, 0.3 over 2x. There's my expression. And here's the headache. Top number squared, if the bottom number, if the concentration are identical, you can square that too, and you can take square root and you'd be done. Life would have been beautiful. You can't do it in this situation. So what do I need to do instead? Well, we need to do the quadratic. So we're going to FOIL it. Yes, FOIL it. You're going to distribute. You're going to make everything equal to 0, like you need to for the quadratic. And there's your A, B, C. And now there's your equation, the glorious quadratic. So substituting into your equation, minus 0.345, plug in all your numbers. You get two answers as usual, which is going to be 1.05, 0.136. Typically for the AP, it's going to be the smaller number. Extremely rare, extremely rare, but we got to cover our bases, right? So plug into both values. You see that 0.136 is indeed the correct one. So as long as you don't get any negative values, your X value is correct and you could roll with it. So there's my answers. Not fun at all. So the question is, how do you avoid a quadratic when this kind of scenario presents itself? We can't do perfect square. Because perfect squares, you're out for this, right? It's your way of avoiding the quadratic. Well, that's what type 4 is. You assume X is so small that we subtract it from the initial concentration, the concentration is not going to change. That's what assuming is. So we're going to basically say our minus and plus X's are 0. Like they don't exist. There's no minus or plus X. Do X's have a value? Of course they do. They can't be 0 overall, but we're going to assume they're so small, we're going to pretend like they're 0. And I'll show you what it looks like. So put initial concentration K in the scientific notation, and if difference in exponent is 3 or more, you can assume X is small. What the heck does this even mean? Well, let's take a look. All right, so here's my K, already in scientific notation. I'm going to put my value for molarity, my initial concentration in scientific notation as well. So that's 2 moles, 5/1 liter, 2 molar. So that's basically 2 times 10 to the 0, right? This is what I'm talking about. When this and this are different from for 3 or more, you could assume X is small. That's your shortcut. Doesn't matter if it's positive or negative. As long as the difference is 3 or more, going either way, you can assume X is small. Watch how this plays out. So here's your setup. You have your 0, 0, because you didn't give any values for it, right? Assume 0. Don't forget the coefficients. It's kind of like with thermal, you know how people keep on screwing up with joules and kilojoules, not making sure they're the same for entropy and enthalpy. That's what this is like in this section. You guys are going to make some silly mistakes, and you have to really be conscious of what you're doing and pay attention to it. So here's my setup. I just carried it down. Write my expression, always. The expression without numbers, always. Plug in my numbers. Realize, oh crap, I can't do perfect square. That sucks. But what I can do is assume X is small. So what does that mean? You assume that when you take 2x away from 2.0, this concentration, it's still going to be 2.0. So anything you're adding or subtracting x-wise, you assume it's negligible. So if the top one, let's say, was 2x plus x, you would say 2x plus x is equal to 2x. You don't ignore the x's. You only ignore what you're adding and subtracting x-wise. Pay attention to that, because students with the other brain fart for this are like, oh, this is minus 2x. The top is plus 2x, plus x. I can't do anything with it. Yeah, you can. Anytime you see a plus sign and whatever number of x, it doesn't matter, you could assume it's negligible and that you could infer that it's going to be the same value afterwards. So it doesn't matter if it's plus, minus, top, or bottom. You assume any addition or subtraction of x's will lead to the same value. You assume for all of them. So now look at the math. A lot easier. What I did, I squared this times this. I got 9.6 times 10 to negative 4. 2x squared, that's the other problem. People forget, you got to square both the number and the letter, times x gives me 4x cubed. So this is where the brain farts come in. Inherently, these are the brain farts. So now I'm going to solve for x cubed. Cube root of the number, 5.13 times negative 4. You can go back and verify. Like right now, if you put 2.00 minus 5.13 times negative 4, you'll get like 1.9999. That's basically 2.0. So your assumption was correct. You don't need to show that though. As long as you did what I just showed you with making sure the exponent's off by 3 or more, you're good to go. It's going to work every time. So here's my numbers. Notice I kept this the same because remember, we assumed it was negligible. So if you decide to put 1.99 here, you look really silly because didn't you just say that it's still going to be 2.0? Don't contradict yourself. They're not going to ask for the reactant anyways. They'll ask for these. This kind of question, I'm going to ask for the concentration of the products. Just don't forget don't forget the coefficient. All right, equilibrium tips. If they don't give you the K, that's automatically a type 1 question. Real simple. So it's one of those system things again, right? You have to train yourself to look at things specifically. If they don't give you a K, you're like, okay, type 1. Beautiful. Handle it. There's no perfect square. There's no quadratic. There's no assuming. It's all for K. That means you have all your concentrations. If they do give you a K, look for type 2 first. That'll make your life easier. Then type 4. And if that doesn't work, you're screwed because the quadratic. Sorry. But let's hope the assumption works because that would be really brutal for them to give that to you on the test. But it's possible. I just want to make that clear. It's possible. Watch out for coefficients that are in 1 since they determine how many x's you have and how many you add or subtract. What I keep on emphasizing over and over again. All right, understanding KSP, the other important concept. And then this is where the twist and turn questions come from, KSP-based questions. These are the ones that are the most brutal, and I could almost assure you they're the most popular for the AP. They love KSP questions. So I'm going to show you how to deal with them. But remember, they're insoluble. So you're going to have to keep that in the back of your head. Only a small amount of this will dissociate, but it kind of like throws everything to a loop. It's like, wait a second, I thought these were insoluble. What the heck? Why is it dissociating? They do, just small quantities of it. So it turns out even insoluble substances do dissociate, and that concentration they produce is called the molar solubility. That is your X. So just remind yourself, molar solubility is code word for X. Please remember that. Because they'll ask you, what is the solubility of this? And students will look like, what the heck is the solubility of this? Or they'll ask you for molar solubility, like, what the heck is, they're asking for X. That's all they're doing. They're looking for X. Important to remember that you have 3 variables in a KSP question, 2 products in a KSP. They will give you 2 of these every single time. Your job, forget the third. As long as you keep that in mind, you're going to avoid silly mistakes. All right, so let's look at how this plays out. So 25 degrees Celsius, the solubility product. So here's your KSP. They give you the K. Yay. Solubility product, constant for strontium fluoride is this. Yay, they give me K for 2 different chemicals. Actually, boo, if they give me K for 2 different chemicals, it's going to be really weird. So first thing I'm going to ask you is for what is the molar solubility of strontium sulfate? What is this? X. That's all you're looking for. You're looking for X. And that's what you want to keep in mind. So what I'm going to do is write my reaction, that's typically the first thing you do, is strontium sulfate. So I have to use a dissociate. That's all the KSP reaction is. Dissociate the compound. What I'm going to do is write my expression. Notice no table. Do not do tables for KSP. They're unnecessary events, at least for the AP. So what I'm going to do is 7.6 times 10 to the negative 7. That's my K for strontium sulfate right here, right? Equal to those two. So they're a 1-to-1 ratio. So I'm going to call both of them X. What if there was 2 here? And this would be 2X, and you would square the number, right? Your expression is extremely important for this because before you plug in numbers, you'll see really quickly, oh, KSP is equal to this times this, and you raise the exponents. You won't make the brain fart. But if you try to do it after plugging the numbers in, you're going to make stupid mistakes. So be careful with that. And I should have really not even put the number down yet, so it could be more clear, but it's okay. So KSP is equal to 7.6 times 10 to the negative 7 equal X squared. Square root both sides. Solve for X. 8.7 times negative 4 moles per liter. That's your molar solubility. So that's your concentration of this and this at equilibrium. That's it. That's all you got to do. Now let's do it for the other chemical. What's the molar solubility of strontium fluoride? Same thing, write the reaction, but notice there's a 2. So there's a 2. Also notice this, their ratio is now 1-to-1. You're going to make the one that has the smaller ratio your X, and the other a multiple of it. So in this situation, this is X and that's 2X. You have to show this. You have to say strontium is equal to X, fluoride is equal to 2X. You have to make it clear. You can't just jump from this to this and say, okay, you figure it out. Don't do that. It's going to cost you. It's not necessary. And high probability is for KSP questions to be on an AP exam, just FYI. So I plugged my X, 2X squared. So here's where the other brain fart occurs for this section. People forget to square the number. They'll do 2X squared as the value. Instead of 4X cubed, they forget you're supposed to distribute to both the letter and the number. So 2 squared is 4, X squared is X squared. And then when you multiply that times X, you get 4X cubed. So then you have to divide both sides by 4 and then cube root it. And then that's when you get this as your X. All right, the last thing was Chatlier's principle. It deals with what happens when a reaction is in equilibrium with stress. Basic idea is that the reaction will respond to the stress by favoring whichever side of the reaction counteracts that stress. So whatever you do to the reaction is going to try to undo it. So here's an equilibrium scenario. If you notice, right now you're at equilibrium because they're all flatlining. You decide to screw with this reaction. You change the concentration. So what do you change the concentration of? How can you recognize that? The one that goes vertical is the one that they messed with. So hydrogen was increased somehow. Okay. First off, it's hydrogen reactant. It's a product. How the heck can we tell? Well, we'll come back to that. Whatever it is, you could tell based on what the numbers happen afterwards. So you see how this goes up and it goes back down. And this will always happen, by the way. Once you stress it, the reaction will counteract that stress by going back down. Why does it go back down? Because it's going to consume it in order to get back to equilibrium, which is back here, and now they're leveled off again. So right now, your Q is equal to K, your equilibrium. Here, your Q is not equal to K, and now you're back to being equilibrium again. When your Q is equal to K, you're equilibrium. So what's going on? So H2 is increased. Now, is H2 a reactant or product? Well, it doesn't really matter in this particular situation. You have to predict that, but you have to be able to distinguish between the reactants and products. At least the chemicals are on one side or the other. And what I mean by that, you don't have to know which one's the reactant, which one's product, but you have to know which ones are on the same side of each other. And how do you determine that? We see how this one went up and then went back down. This one went up, right? If this one went up, that means it's on the opposite side of the arrow. Because if it's on the same side, whatever you do to this chemical, you know, the going down part, you also have to do to this chemical, but that's not what's happening. What's happening for this particular situation is that as a result of this going down, this is going up. And you notice that the I2 does the same thing. So I2 is the other reactant. You could balance it real quick by putting 2 here. And that kind of explains why the ratio, the way it looks, is a little different. we're not going to focus on the ratio right now. The main thing you want to pay attention to is that whatever chemical there changes and go vertical and then go down, back down right afterwards. Whatever's on the same side of it, it's going to react the same way. This is when I increase the concentration of a chemical. It will go back down with it. That's what this does. And whatever's on the opposite side will go up. So you stress this reaction out by increased amount of hydrogen. So what did the reaction do? It said, okay, I'm going to use up that hydrogen to make a more HI. But in order to do that, I have to use up H2 and I2. And that's why both of these go down. That's why HI goes up. So here's your principles. Effective concentration done by adding an ion that is identical to a reactant or product in the reaction or will react with a reactant or product. So those are your possible scenarios for that. So let's talk about the different things. One, decreasing concentration. So whatever side you decrease, the reaction is going to counteract that by making more of it. So for that previous example, let's say I decrease the amount of hydrogen, what's the reaction going to do? Make more of it. So it's going to shift in that direction and make more of it. Remember, the big picture here is that the reaction is reversible. So you can easily make either more products or more reactants based on whatever's happening. So when you stress a reaction to equilibrium, if you decrease the concentration of reactant, for example, your reaction will shift to make more reactants. So favor the reactant side temporarily. If you take away a product, what's going to happen? The reaction is going to counteract that by producing more product. It'll shift toward the products. So you're basically shifting it toward the reactants or products to balance out the stress. And that's the basic principle of the Chatlier. So increasing concentration, reaction with stress is shifted in favor of the opposite direction. So what I did in the previous example with the hydrogen, you saw that as I increased it, how did the reaction shift? It shifted in the opposite direction in order to consume that. And that's why the HI went up and that's why the I2 went down. So let's try some questions. What would happen if you increase the concentration of hydrogen gas? Hydrogen is a reactant. I make this go up. So what's the reaction going to do? Opposites, right? If I increase this, I'm going to try to eat this up. And how do I eat this up? Going toward more products. So you're going to favor more products and consume the hydrogen and the nitrogen technically too. I do want to make that clear. Both of them are going to be consumed. What would happen to the concentration of ammonia? Well, if you're shifting toward it, you're going to make more of it. So whatever you shift toward, you're going to make more of it afterwards. That's just common sense. What would happen to the concentration of nitrogen? Well, in order for this to shift to the right and produce more ammonia, you need nitrogen and hydrogen. So nitrogen can go on for the right. So if you decrease the amount of hydrogen to go to the right, you also decrease the concentration of nitrogen. What happened to the concentration of nitrogen decrease? Well, if this decreases, you're actually going to try to make more of it. So it's going to shift to the left, shift toward the reactants. And please don't use left and right. Use favor reactants, favor products for your explanations, just FYI. What happened to the concentration of hydrogen? Well, because I favored the reactants and made more of them, and hydrogen's a reactant, it's going to go up. What happened to the concentration of ammonia? Well, in order to go to the reactants, you're going to consume products. So, of course, the amount of ammonia is going to go down over time. So those are the scenarios that are possible. All right, effective pressure. When you change the pressure, you need to counteract that. So let's say I decrease the pressure. So what's the reaction want to do? Get it back to originally was. So let's say it was a 1 atmosphere. I'll make it go down to 0.5 atmosphere. So how's it going to counteract that? How's it going to deal with that stress? Well, it's going to try to get its pressure back up. So how's it going to do that? It's going to shift to the side that has more moles of gas. And this is only significant for gas, by the way. If you don't have a gas, or if there's no gases here in the reaction, pressure and volume don't do anything. Just keep that in mind. Pressure can be changed by changing the volume of the container or by adding an inert gas. So typically it's the volume scenario. They'll tell you the volume goes up or down, and then you're supposed to know, oh, pressure and volume are inversely related. So if I make the volume go down, I make the pressure go up. So you need to make that correlation in your head. And what I was suggesting, if they give you a volume question, switch it to a pressure question right away. So that way it's easier to manage, and less thing to memorize. I mean, instead of trying to say, okay, well, volume goes up and don't do that. Whatever volume they give you, up or down, change it to pressure question and memorize the pressure scenarios I'm about to show you. So if the volume goes up, pressure goes down. If the volume goes down, pressure goes up. Simple as that. So I decreased the pressure. You know, however I did it, maybe I increased the volume, right? I may put it in a bigger container so the pressure went down. Okay, wonderful. Now what is that going to do? And for those who trying to remember how that correlation works, remember, if you have more space available, there's going to be fewer collisions, and collisions what dictates pressure. So less collision means less pressure. That's the connection in all this. So anyways, with this, you decrease the pressure. So what's the reaction going to want to do? It's going to want to try to make more. So let's say this is the reaction. H2 plus N2 produces NH3. It's a reversible reaction, so I should put both arrows. Balance this and balance this. Okay, these are all gases. Okay, first off, they have to be gases for any of these pressure volume stuff to happen. So look what happens. You have 4 ammonias initially. Remember, it's just a balance. It's a recipe. So this is double the recipe. Before you like, why is there 4? But just roll with it for now. Okay, so what happens? You notice as you decrease the pressure, what happens? You have less moles of ammonia, right? So what do? You want to favor the side that's going to get the pressure back to where it's supposed to be. So how do you do that? Take a look. You have 2 moles of gas here. You have 4 moles of gas here, right? 4 versus 2. If I want to increase the pressure, am I shift to the side that has more moles of gas or less moles of gas? That's what you have to ask yourself. Well, if you have more moles of gas, you have more collisions, right? More collisions is more pressure. So if what happened is that you decrease the pressure, the way that the reaction is going to react to that, it's going to increase the pressure back up. And the way it's going to do that, it's going to favor the side that has more moles of gas. So that's why you see more nitrogen and hydrogen and less ammonia. Is because what the reaction is doing is saying, okay, you're going to stress me out by lowering my pressure. Okay, fine. I'm going to produce more moles of gas, and that's going to create more pressure. Look at the number of particles up here relative to here. There's way more here. So that's why the pressure for this scenario is going to go back up, and now you're going back to equilibrium. So that's how you counteract changes in pressure. You shift to the side that has more moles of gas. When you decrease the pressure, you shift to the side that has more moles of gas. What about when you increase the pressure? You shift to the side that has less moles of gas. Which side has less moles of gas? The ammonia side, right? So you see how there's more ammonia now? Why? Because your reaction is going to counteract the stress by shifting to the side that has less moles of gas, which is 2, so there's less collisions. Look at the number of particles here and the collisions that are possible, and look here. That's how you deal with pressure questions and volume questions too. So let's take a look at this scenario. Let's take a look at this. What you want to do is count your moles of gas. You have 2 here, 4 here. It's the same scenario we just did a second ago. So which direction would shift if the pressure increases? You shift it as less moles of gas, which is going to be the product side. And then for the second scenario, which direction would we favor if the pressure decreases? The side that has more moles of gas, which is obviously that. And which direction would the reaction favor the volume increases? So volume going down, meaning that pressure goes up. Pressure goes up, you favor the side that has less moles of gas, which is once again the product side. That's why it's important you shift it to a pressure question. It makes it easier to memorize. All right, temperature. Temperature decreased. What happened? So there's your reaction. You can see the amount of SO2 went down. The amount of O2 went down. These are both reactants, right? These both went down as a result of this. But your SO3 went up. Now, why is there not this little thing? Because you didn't change the concentration of a chemical, you changed the temperature. Just like you change the pressure, it's not going to have the little vertical line for a chemical. It's just going to be a really quickly, at equilibrium, shift to whatever direction you want to. The concentration of this goes down right away, and the concentration of the other chemicals. Now, if you look at this carefully, what you hopefully will see is that the concentration of this decreased a lot faster than this. Why is that? There's more moles of it. And for those wondering, well, wait a second, why are they not the same height? I mean, what is this? They're 2 different concentrations to start out with. So this could be like 1 molar. This could be like 2 molar. They don't have to have identical concentrations. You want to be clear about this. The amount of reactant you're starting with is variable. It doesn't have to be a set number. So in this situation, you're starting out with more SO2. Wonderful. But you're also using more of it in the reaction. So you're using it twice as fast. So that's why this line has to be lower than this line. Look at the distance between here and here versus here and here. You can see that this obviously went down much faster. Please make sure you understand that. You have to use the coefficients in that sense. And same with SO3, you notice that this is basically equivalent to how steep this is in terms of increasing in this time. So the question is, why is any of this happening? Here's why. If it's exothermic reaction, which is what this is, because energy is on the product side, put the word temperature on product side. Why? Because you're going to treat it like a chemical. So in this situation, because it's exothermic, so let's say that they told us its enthalpy was negative 400 kilojoules. Once they said negative, your mind should be like, okay, temperature on the product side. That's how I'm going to deal with it. Same sense, if it was an endothermic reaction where the enthalpy was positive, you put temperature on the reactant side. Now, why would I want to do any of this? Because now I'm going to treat the word temperature like it was a chemical. So if they tell me the temperature increases, I'm going to look at temperature like a chemical and say, well, temperature increases, we shift to the side that's opposite. Just like you would do for a concentration question, right? Because if this goes up, what's going to happen? You can go in the opposite direction. Well, if temperature decreases, well, I'm going to shift to the side that the temperature is at because I want to make more of it. So what's going on here? Which way did I favor? My SO2 and O2 went down, right? So that means I'm favoring the product side. Product went up. So what did they do? What was the stress? Temperature decreased. Why? Or how can you tell that? Well, one, it tells you. But the other reason is because you favor the product side and temperature's there. Remember, whatever side the chemical is being decreased, you're shifting in that direction. So the fact that you are favoring products indicates that you're favoring the side that's going to make your temperature go back up. So that means what you're doing stress-wise, you're decreasing the temperature. That's the stress. So the opposite of decreasing the temperature is to increase the temperature. No way to do that is to favor the products. So if it was endothermic, by the way, put temperature on reactant side. That's how you'll deal with it. And that's equilibrium in a nutshell.